Thus far, we have learned the vocabulary to describe position, velocity, and acceleration. We've also learned how to graph those three kinematic variables as well. In this important section, we learn how to write down the equations for their motion. These three equations will be called the kinematic equations because they relate the kinematic variables. The most important thing to remember about these kinematic equations is that they are only valid if the acceleration is constant. If the acceleration is not constant, then calculus must be used. So let's get started looking at these. The first kinematic equation gives a formula for position. In this case, what it really gives us is position as a function of time. In order to find the position at any time, all we need to know is the acceleration, which is constant, the initial velocity, v sub 0, and the initial position, x sub 0. The next kinematic equation gives a formula for velocity. And what it really is giving us is velocity as a function of time, so that if we know the acceleration and we know the initial velocity, then we can find the velocity at any time. The final equation connects position and velocity, and this third kinematic equation is useful when time is not relevant. As you can see in the equation, there is no t variable, and so this formula will be most useful when we need to connect the velocities and the accelerations and the positions without knowing time. As this warning here says, as one final time, the acceleration must be constant. And I emphasize that again because the AP exam loves to pick problems where the acceleration is not constant. And these problems often fool students who use the kinematic equations even though they are not valid. So for a little while, most of our accelerations will be constant, but you shouldn't assume that that's always the case. And as you go on later in this course, it will be very important to check if the acceleration is constant before you start using these equations. Let's go ahead and look at an example of applying these kinematic equations. In this example, we're looking at a car that's initially at rest and accelerates on its way. The first question asks, what is the position after 10 seconds? In this case, you should start thinking that we should be using the first kinematic equation because we're looking for position and it's giving us information about time. So let's go ahead and get started solving it. The first thing we should do is write down the equation that we're using. X equals 1/2 at squared plus v naught t plus x naught. Then it's just a simple matter of plugging in the values that we know. We know the acceleration is 4, that's given to us in the problem. We know the time is 10, that was also given to us. We know the initial velocity is 0 because it said the car was initially at rest. We multiply that by the time. And then finally we need to plug in the initial position, which is 0 because it was located at the origin to begin. Now we just simplify and find out that our position at 10 seconds is 200 meters. Part B has us finding the velocity at the same point in time, 10 seconds. In this case, we're trying to find the velocity and the information that's given to us is time, so we should use the second kinematic equation. Writing it down, v equals at plus v naught. Now we just need to fill in the values that were given. A is 4, t is 10. Again, v naught is 0 because it was at rest initially. Now we just need to simplify and write down our answer, in this case, 40 meters per second. In part C, we're trying to find the velocity where all that's given to us is the position, 100 meters. In this case, it makes the most sense to use the third kinematic equation because time is not relevant here. So we write out down the equation that we're given, v squared equals v naught squared plus 2a delta x. And now we need to fill in the information that was given to us. V naught is 0, a is 4, and in this case, the change in position was 100 meters. Now we just do a little bit of simplification, and finally we can solve for our answer, 28.3 meters per second. This next example will show us how to use the kinematic equations in a situation that's a little bit less straightforward. To begin, we need to find the distance this train travels in 5 seconds. So we'll go ahead and write down our kinematic equation, and we'll use the first one because what we're given is time and we're trying to find position, which will lead us to distance. In this case, we write down x equals 1/2 at squared plus v naught t plus x naught, we fill in the information that's given to us. A was given to us as 2, our time is 5, the V0 is 0 because it was initially at rest, and then finally we need to substitute an X0. Now it didn't tell us where it was located to begin with, but we can implicitly make the choice that it was at the origin, so we set our initial position to 0. That finally gives us the position at 5 seconds as 25 meters. But because we started at 0 and we ended up at 25 meters, then we know that the distance we traveled is in fact 25 meters, and so that's the correct answer. In part B, we're going to again use the same equation, x equals 1/2 at squared plus v0 t plus x0, but our equation is not going to give us the answer directly. Instead, what we're going to do is find the position at 10 seconds and use that information to answer the question. Using the same values as before, a is 2, v0 is 0, and x0 is 0, we fill in our information, and what it tells us is that the position after 10 seconds is 100 meters. Now that's not the answer because the question is asking for something different. But it does tell us that from part A we know that it travels 25 meters in the first 5 seconds, and so it must travel 75 meters in the next 5 seconds, which is to say, in the same amount of time it travels 3 times farther. And again, the reason it travels 3 times farther is because it's accelerating. Let's look at this next example of a speeding car. This problem is a good use of using the kinematic equations to solve a more complex problem. In this case, what we're given is information about 2 different cars. So let's draw a picture because it's starting to get a little more complicated. We just draw the police car and the speeding car and just a few dots just to illustrate that they're both moving to the right. Now what we want to do is we want to write down one equation for the position of the speeder and one equation for the position of the police car. So to write down the position equation for the speeder, we're going to use the first kinematic equation, x equals 1/2 at squared plus v0 t plus x0. And now we fill in the information that's relevant for the speeder. Well, the speeder is traveling at a constant speed, so its acceleration is 0. Its initial velocity is 25, and we can assume that it started at the origin, and so we finally get an equation for the speeder's position as 25t. The next thing we'll do is write down the position for the police car, and this time we know that the police car accelerates at 5 meters per second squared, but was at rest to begin with. So once we simplify everything, that gives its position as 2.5t squared. Now, we need to translate the problem we're asked into mathematical terms. And the problem we're asked to solve is when does the police car catch the speeder? And so to write that down, that's really the question, when is x sub s equal to x sub p? That's when their 2 positions are going to be equal. And so we substitute them in, and we have 25t equals 2.5t squared. Now this is a quadratic equation, and therefore has 2 solutions. I think it's pretty clear that if you plug in t equals 0, this equation will be valid. And that's because they were together to begin with. But the point that we're really looking for is the next solution, and that's when t equals 10. And so when does the police car catch the speeding car? After 10 seconds. And now in part B, to figure out how fast the police car is, well, we just need to use the second kinematic equation, v equals at plus v0, and plug in the relevant information for the police car in order to solve for its velocity. In this case, we simply fill things in, and what we get is 50 meters per second. Finally, it's important to be able to look at these equations and also recognize what type of motion is happening, and to be able to describe that motion in words. That's what this example is asking us to do. In this first example, we're given an equation that describes the position of a dog as a function of time. To understand how to describe the motion of this dog, let's compare the equation that we're given, x equals 2t squared plus 3t plus 1, to our first kinematic equation, x equals 1/2 at squared plus v0 t plus x0. And once we write them next to each other, it becomes pretty clear that the coefficients are going to give us the relevant values that we need. 2 is going to be equal to 1/2 a, 3 is going to be equal to v0, and 1 is going to be equal to x naught. So if we write these down, then we can solve for these variables. A is equal to 4 meters per second squared, v naught is 3 meters per second, and x naught is equal to 1. Now if we want to describe this situation in a sentence, we could write something like, the dog starts at 1 meter in the positive direction at a speed of 3 meters per second. It then accelerates at 4 meters per second squared. In part B, we're given a similar problem to solve, but this one doesn't have a t squared term. Now that's not really a problem at all, because what it just means is that our t squared term has a coefficient of 0. So if we write that down, we can solve for our acceleration, initial velocity, and initial position. And as you can see here, this gives that our acceleration is 0, our initial velocity is 5, and our initial position is 2. And if there's no acceleration, that means this is traveling at a constant velocity. So we could write a sentence that looks kind of like, the cat starts at 2 meters in the positive direction and travels at a constant speed of 5 meters per second. In part C, we can try to figure out how does this fit in with the kinematic equations we've seen before. But here immediately recognize that this is a degree 3 polynomial, which is to say that the t is to the third power. In this case, what that means is there is no way that this could come from our kinematic equations. So what we must conclude is that the acceleration in this case is not constant. And this would be the type of situation that you would need calculus to investigate, and we'll discuss that in a future video.